What I hope to do in this video is prove the angle addition formula for sine, or in particular, prove that the sine of x plus y is equal to the sine of x times the cosine of sine of x times the cosine of y plus cosine of x times the sine of y. And the way I'm going to do it is with this diagram right over here that you can kind of view it as it has this red right triangle. So it has this right triangle here that has a hypotenuse of 1. You could say this triangle ADC. It has it stacked on top of its base is the hypotenuse of triangle ACD, which I could, let me outline it in blue since I already labeled the measure of this angle as being y. So we have ADC is stacked on, or this AC, which is the base of triangle ADC, is the hypotenuse of triangle ABC. They're just kind of stacked on top of each other like that, just like that. And the way I'm going to think about it is, first, if you just look at this, what is sine of x plus y going to be? Well, x plus y is this entire angle right over here. And if you look at this right triangle ADF, we know that the sine of an angle is the opposite side over the hypotenuse. Well, the hypotenuse here is 1. So the sine of this is the opposite over 1, or the sine of this angle, the sine of x plus y, is equal to the length of this opposite side. So sine of x plus y is going to be equal to the length of segment DF. The length of segment DF. And what I'm going to try to do is say, well, okay, length of segment DF is essentially what we're looking for, but we can decompose the length of segment DF into two segments. We can decompose it into length of segment DE and the length of segment EF. So we could say that DF, which is the same thing as sine of x plus y, the length of segment DF is the same thing, is equal to the length of segment DE plus the length of segment EF And EF is, of course, the same thing as the length of segment CB. That ECBF, this right over here, is a rectangle. So EF is the same thing as CB. So this thing is going to be equal to, DE right over here, length of segment DE, plus the length of segment CB, So once again, the way I'm going to address this, I'm saying, the sine of x plus y, which is the length of DF, and DF can be decomposed as the lengths of DE and CB. Now with that as a hint, I encourage you to figure out what the length of segment DE is in terms of x's and y's and sines and cosines, and also figure out what the length of segment CB is in terms of x's and y's and sines and cosines. So try to figure out as much as you can about this, and these two just might fall out of that. So I'm assuming you've given a go at it. So now that we know that sine of x plus y can be expressed this way, let's see if we can figure these things out. And I'm going to try to address it by just figuring out as many lengths and angles here as I can. So let's go to this top red triangle right over here. Its hypotenuse has length 1. So what's going to be the length of segment DC? Well, that is the opposite side of our angle x. So we know sine of x is equal to DC over 1, or DC over 1 is just DC. So this length right over here is sine of x. And segment AC, same exact logic. Cosine of x is the length of AC over 1, which is just the length of AC. So this length right over here, segment AC, is just its length is cosine of x. So that's kind of interesting. Now let's see what we could figure out about this triangle ACB right over here. So how could we figure out CB? Well, we know that sine of y, let me write this here, sine of y is equal to what? It's equal to the length of segment CB over the hypotenuse. The hypotenuse here is now cosine of x. And I think you might see where all of this is leading. And at any point, if you get excited, pause the video and try to finish the proof on your own. So the length of segment CB, if we just multiply both sides by cosine of x, the length of segment CB is equal to cosine of x times sine of y times sine of y, which is neat because we just showed that this thing right over here is equal to this thing right over here. So to complete our proof, we just need to prove that this thing is equal to this thing right over there. If that's equal to that and that's equal to that, well, we already know that the sum of these is equal to the length of df, which is sine of x plus y. So let's see if we can figure out if we can express dE somehow. Now, what angle would be useful? Well, somehow we could figure out this angle up here, or maybe this angle. Well, let's see if we could figure out this angle. If we could figure out this angle, then dE we could express in terms of this angle and sine of x. Let's see if we can figure out that angle. So we know this is angle y over here, and we also know that this is a right angle. So EC is parallel to AB. So you could view AC as a transversal. So if this is angle y right over here, then we know this is also angle y. These are, once again, well, notice this is, if AC is a transversal here and EC and AB are parallel, then if this is y, then that is y. Then if that's y, then this is 90 minus y. 90 minus y. And if this is 90 degrees and this is 90 minus y, then these two angles combined add up to 180 minus y. And if all three of these add up to 180, then this thing up here must be equal to y. Validate that. Y plus 90 minus y plus 90 is 180 degrees. And that is useful for us because now we can express segment DE in terms of y and sine of x. What is DE to y? It's the adjacent angle. So we could think of cosine. We know that the cosine of angle y, if we look at triangle DEC right over here, we know that the cosine of y is equal to segment DE over its hypotenuse, over sine of x. And you should be getting excited right about now because we've just shown, if we multiply both sides by sine of x, we've just shown that DE is equal to sine of x times cosine of y. Cosine of y. So we've now shown this is equal to this. We already showed that CB is equal to that. So the sum of DE and CB, which is the same thing as the sum of DE and EF, is the sine of x plus y, which is that over there. So we are done. We have proven the angle addition formula for sine.